Okay, let's get started. Number one, the figure represents the position of a particle as it travels from the x-axis. What is the average velocity between t equal to 1 and t equal to 4? Now, you just have to use the definition of, let me get this to be larger. Okay, the definition of average velocity, V average is x final minus x initial over t final minus t initial. So in this case, t final is 4 seconds, t initial is 1, and at t equal to 4, reading from the graph, the x value is 2, so x final is 2, and at t equal to 1, x initial is 0. So it's 2 minus 0, and you get 2/3. So that would be 0.67. Okay, number 2, you're told that an astronaut stands by the rim of a crater on the moon where the acceleration due to gravity is 1.62. Now, this is not the same as the Earth where it is 9.81 meters per second squared, but this one is 1.62. But other than that, it's the same kind of a problem. To determine the depth of the crater, she drops a rock and measures the time to hit the bottom. So if you start out here and you let it drop, you're told that the depth of the crater is 120 meters. How long does it take? They want to know time. And when you drop, it means that your initial velocity is 0. If you call the downwards direction positive, then the equation of motion that you would use is x equal to x naught plus v naught t plus 1/2 at squared. X would be 120 since you call downwards positive. Initial is 0. Initial velocity is 0. And your A is positive, 1.62 t squared. The only unknown here is t, and when you run to your calculator and work it out, you'll find that it takes 12.2 seconds. Number 3, vector A has a magnitude of 16 meters and is pointing eastward. So I'm going to draw that. Pointing eastward, 16 meters. Now, if you rotate it counterclockwise by an angle of 110 degrees, counterclockwise means in this direction. So you rotate it 110 degrees. So now the vector is this one. Okay, they ask for the magnitude of the component of this rotated vector along the west direction. Now this is the west direction. And basically what they want is the component of this vector. So that means they want this distance. They say the magnitude, right? So it's a distance. And this angle is 70 degrees. And it's adjacent to the hypotenuse. So adjacent is cosine. Then the component is length times by cosine of the angle. And from your calculator, you will work it out to be 5.47 meters. Okay, next problem, number 4. You're told that vector A has components ax greater than 0 and ay less than 0. The angle this vector measured counterclockwise from the positive x-axis. So the first thing is to sketch the vector. Now, if you have a positive x component and a negative y component, this is what the vector would be. The sum of the x and y component would be this vector pointing from the origin to this direction, like that. Therefore, the angle that this vector makes measured counterclockwise from the positive x-axis. This is the positive x-axis. Counterclockwise means this angle. Now, You start out at 0, and as you go, this is 90 degrees. And when you get to here, that's 180. This is 270. And finally, when you get back here, it will be 360. So you are between 270 here and 360. So the answer is D. Okay, next problem, number 5. It says, for general projectile motion, which statement is true when the projectile is at the highest point? So before you even read the answer, maybe you look at what you know about the projectile motion. It looks like this is a parabola, and they are talking about at the highest point. This is the highest point. Now the highest point is defined to be, or is the point where you have no y component of velocity, but you still have x component of velocity. Therefore, it is the same value as the initial x component of velocity at this point. Right? It doesn't change. No matter where you go along the curve, the x component remains the same. But the y component at the very top is 0. Now, you also know the acceleration. The acceleration is 9.8 downwards. Now, this is true everywhere along the curve as well. So there's nothing special about the top. The top is only defined by the y component being 0. So this is G here, and this is V. So maybe I'll write them as vectors like that. So let's read. A, it says its velocity is perpendicular to the acceleration. Well, that's true. This is 90 degrees. So this is an answer. Let's make sure the others are not correct. So this is correct. Part B says its velocity and acceleration are both 0. No, its acceleration is not 0, and neither is its velocity. The horizontal and vertical components of its velocity are both 0. Only the vertical is, the horizontal isn't. Its acceleration is 0. Its acceleration is not. It's always 9.8 downwards. Okay, next problem. A ball is thrown at an angle of 40 degrees above the horizontal with an initial velocity of 22 meters per second. So, typical projectile motion problem. 40 degrees and 22 meters per second. That's the initial velocity. What is the range of the ball? Well, you can do it the long way by looking at the time it takes for it to get back to the same level. And once you know the time it takes to get there, this is the range. And the range is just V0, which is 22 meters per second, times by cosine 40 degrees, times by the time of flight. And you can work out the time of flight by setting y equal to 0 in the y motion. Now, you can also use the equation for the range, for horizontal range, which is derived, and it is given by the formula V0 squared over G sine 2 theta. So in this case, it is 22 squared divided by 9.8 times by sine of 2 times by 40 is 80. And running to your calculator and working it out, you find that it is 48.6 meters. That's the range. All right, next problem. A horse pulls a cart with a force F. As a result of this force, the cart accelerates with constant acceleration. What is the magnitude of the force the cart exerts on the horse? So there are two bodies here. This is the cart, and this is the horse. They both look like potatoes to me. So the horse is pulling on the cart, and therefore it exerts a force in this direction on the cart. And as a consequence, the cart would start accelerating in this direction. Now, that's not the question. The question is, what is the magnitude of the force that the cart exerts on the horse? So that's the reaction pair. The horse would experience a force in this direction. This is the reaction pair to the action, which is the horse pulling the cart. And by Newton's third law, the magnitudes of these two forces, the action-reaction pair, are the same. So the answer is equal to the magnitude of F. Now, the horse actually feels the effects of the cart, feels that it is pulling the cart due to the force that the cart exerts on the horse, and suddenly that will be pulling the horse in this direction. Okay, next problem. A 40-kilogram box is being pushed horizontally along a smooth horizontal surface. The pushing force is 15 newtons directed at an angle 15 degrees below the horizontal. So what you have is a box, and you push down on it 15 newtons. And this is not horizontal or vertical, but at an angle. The angle you're told is 15 degrees. Okay, now for this problem, you know that the only motion possible is in the x direction, this way. And because of that, you don't have to consider the y motion at all. You just apply Newton's second law. Sum of all x forces is equal to m times by the acceleration in the x direction. Okay, and that's the acceleration of the box, because we know it moves only in the x direction. Now, since there's only one horizontal force, the weight and the normal force, I can call that the normal force now, and the weight, they're both perpendicular to the x, so you don't have to worry about it. Now, if you look at this force of 15 newtons, its x component is the adjacent side to the 15 degrees. So the component would be 15 cosine 15 degrees. This would be equal to the mass, which is 40 times by the acceleration. And running to your calculator and working it out, you find that it is 0.362. That's the answer. Okay, then let's get to the problems. Now, the problems are like this. They're a little longer, but not that much more difficult. So let's read it. A speeding car is driving north with a speed of 35 meters per second. And unbeknownst to the driver, passes a speed trap. So there, let's sketch it. You have something going north. This is the speed trap here. And the copper is hiding behind the bushes over here. So this driver is speeding, moving along at what we would presume to be a constant speed of 35 meters per second. So, and it passes the speed trap. The traffic cop registers the speed and takes 4 seconds to get the police car onto the freeway, on the highway, to give chase. So after the car passes the checkpoint here, the cop takes 4 seconds to get to it before it starts chasing after the car and sounding the siren. So this part of the journey is one at constant velocity of 35 meters per second for 4 seconds. Now, the police siren comes on at this moment, that is after 4 seconds, and the obedient driver immediately applies the brakes and slows to a stop. So this, upon hearing the siren 4 seconds later, the driver applies the brakes and slows down. So this part of the motion is deceleration. Now, deceleration means that you're slowing down. Since your motion is in this direction, if I call that the positive direction, what that means is A is minus 5 meters per second squared. So there are two distinct phases to the motion, right? The first part, this part here, is one of constant velocity. The next phase, the part here that I draw in red and in black, that's one where you move at constant acceleration. Yes, it's negative, but it's constant. So let's see what they want. They say we want to find how far from the speed trap the car is when it is stopped. So basically what they really want is this total distance. So let's see what is being asked. Part A says, how far has the car traveled prior to applying the brakes? So they're referring to the blue part of the motion. Now you're traveling at constant speed, 35 meters per second for 4 seconds. So that would be, distance travel would be 35 times 4. 35 times 4, you work that out, that will be 140 meters. Now, if you are curious, you actually can use the equations of motion for constant acceleration to solve this part of the problem. You just have to remember that over here, A is equal to 0. And if you put A equal to 0 in all those equations of motion, everything would work out. Part B, what are the initial and final speed of the car? Now, the initial part of the motion, the car is moving at 35. So the initial speed is 35. And the final speed, now because it is stopped, the final speed is 0. Now, part C says, what is the displacement of the car during the deceleration period? Now, as far as you are concerned, you can look at this as the beginning of your motion, this part after 4 seconds. So you can call this part here your origin, so that's where x is 0, x0 is 0, right? And then you have your acceleration, and you have your initial velocity. Your initial velocity, which is this point, is the 35 meters per second that is asked in part B, and your final is 0. Now, what they ask for is displacement. Displacement is really x minus x naught. Now, if x naught is over here, and if you think of this as 0, then you're just looking for x, which would be the distance from where the car is stopped here to where the car was starting the deceleration, which is this part of the beginning part of the deceleration. Now the equation one, if you look at the many equations, the one that would solve this is the one that says v squared is v naught squared plus 2a x minus x naught. Okay, your final velocity is 0, your initial is 35, you square that, plus 2a. Now a in this case is minus 5, and x is your final position, and x naught you can call that 0. Doesn't matter because what you really are after is x minus x naught. So from here you find that because of the minus sign, x will be positive, because if you call this part here, the beginning of the journey, deceleration 0, and this is the positive direction, then clearly x, which is this value, is positive. So if you play everything right, you will get a positive answer, and this is a positive answer. X is going to be 35 squared divided by 2 times 5, which is 10. And if you run to your calculator and work it out, it will be 122.5 meters. Now, part D asks, how far is the car when it is stopped from the speed trap? In other words, they want to know this distance. Now, in this part of the journey at constant speed, part A shows you this part of the journey. Part A shows you travel 140 meters. And then you travel an additional 122 meters. So the total distance that you travel is 262.5 meters. So that's how far the car is stopped from the speed trap. Okay, last part here. It says, finally, if the driver passes the speed trap at noon, what time is it when it comes to a complete stop? Give answer in so many seconds past noon. Okay, there are two different types of journey. The first one of constant velocity, 35 meters per second, took 4 seconds. Now you have to add to that the time for the deceleration phase. So you want to know t for the deceleration phase. So how do we calculate that? Well, there are several equations you can use. The easiest one is to use v is v naught plus at. And what this gives you is your final velocity is 0. Your initial is 35. Your acceleration is minus 5, and then t. And solving this, clearly t is 7 seconds. Therefore, the total time between passing the speed trap and stopping is 7 seconds plus 4 seconds is 11 seconds. So it will be 11 seconds past noon. That's when you're stopped. Okay, next problem. It says the following. Huck Finn decided to throw an egg against the wall of the house of the local bully. He threw the egg with an initial speed of 16 meters per second at an angle of 40 degrees above the horizontal. So typical problem, you have projectile motion 40 degrees, 16 meters per second. All right, now you're told that the wall is 8 meters from Huck Finn when the egg was released. Okay, so this is the point where the egg is released, and you have a wall, presumably the house. This is 8 meters away. Okay, now the question is, how much time did it take after it was released for the egg to hit the wall? Now, looking at this, you know that when it hits the wall, it has traveled a distance of 8 meters in the x direction. So we say x is 8. We don't know what y is, but we know x. Now, if you consider the x motion, it's very simple. It's constant velocity. It says x is v naught cosine theta times by t. So if you want to find the time to hit the wall, all you do is you say x is 8, v naught in this case is 16, times by cosine of 40 degrees, multiplied by t, and you can easily solve for this. And when you do that, what you find is that the time taken is 0.65 seconds. Okay, now they ask how high above the point of release did the egg hit the wall? So basically they're asking, right, this is the trajectory of the egg, and they want to know how high above the point of release. So they want to know the y value, in other words. So another of those equations of motion, when you look at the y motion, one of the equations is y is equal to v naught sine theta times by t minus 1/2 gt squared. So in this case, you want to find y, you know v naught, you know theta, and part A solved the time for you. 0.65 minus 1/2, 9.8, 0.65, and you square that, and if you just run to your calculator and work everything out, what you find is that this is 4.63 meters. Okay, next part of the problem. What is the speed of the egg when it hit the wall? Remember that the egg has both a horizontal and vertical component of velocity, and speed is the magnitude. Well, it basically gave everything away. First of all, what is v sub x? V sub x never changes. It's v naught cosine theta, which is 16 cosine 40, which if you run to the calculator is 12.3 meters per second. What about v sub y? Once again, you have a choice of equations. Because you know the time, the easiest one is v naught sine theta minus gt, which is 16 sine 40 minus 9.8 times by 0.65. That you got from part A, the time. And if you run to your calculator, again, you have 3.89 meters per second. So the magnitude of your velocity, the speed, v, is the square root of v sub x squared, which is 12.3 squared, plus v sub y squared, which is 3.89 squared. And from your calculator, it will be 12.9 meters per second. Okay, the last part is this. Was the egg going up or coming down when it hit the wall? Justify your answer. Now, as you might remember, anytime you have a curved motion, the velocity is tangential to the curve. That's why at the very top it's horizontal, and as it is falling down, it is now pointing downwards. So what you notice is that for an object that is rising, that is going up, it has a positive y component of velocity. For an object that is falling, you always have this x component, but its y component is negative. Now we worked out in part C that the y component is positive. So v sub y is greater than 0 implies that the egg is going up. Okay, last problem. The figure shows two teenagers pulling on a 4-kilogram sled on which rests an 18-kilogram child. Both teenagers pull with a force of 55 newtons at an angle of 35 degrees relative to the direction of motion as shown. Now, in addition, the snow exerts a retarding force of 57 newtons on the sled that points opposite to the direction of motion. Retarding means slowing down, and if it's slowing down, it will be opposite to the direction of motion. So basically, telling you that it points opposite to the direction of motion is actually redundant, but it's just made to be sure that you are clear about the whole picture. Now, part A says draw a free body diagram. Now, we're going to look at it from an edge, from the top view. So the top view, you have an object. What is this object? It's a point. We represent it as a point. The object would be the 18-kilogram child plus the 4-kilogram sled. Okay, so the total mass actually is 18 plus 4, 22 kilograms. Now, this mass, this object, experiences two forces from the teenagers pulling. They are both pulling with a force of 55 newtons. So let's draw that in. And both these forces make an angle of 35 degrees with the direction of motion. So they show you that this is the direction of A. That means that's the direction of your net force. Hopefully that's what it works out to be. Now the drawing shows you that you also have a third force due to the effect of the snow on the bottom of the sled, and this force is pointing in the opposite direction, 57 newtons. So those are the three horizontal forces acting. Now, since we are looking from the top down, if you really ask what about the weight, it is pointing into the paper. And what about the normal force? There will be a force pointing up from the snow, from the paper if you want. And these two forces cancel each other, and that's why your sled is not lifting up into the air or burrowing into the snow. Okay, let's see what part B asks. Part B says, find the acceleration of the sled and child. Now, in this case, we have to apply Newton's second law. Now, this is two-dimensional. Hopefully, if the drawing is correct, if I call this my x and that my y, I would find out that A only has an x component, but let's see that it works out. Now, if I look at the y component, it would go something like that, right? Sum of f sub y equal to m a sub y. And what this implies is, if you look, this force has a y component that is this way, upwards. And it is opposite this angle, 35 degrees, so you know it is sine. That means it is 55 sine 35 degrees. Now, likewise, this second force from the second teenager, it has a y component that is pointing down. And because it's pointing down, you say it's minus, you add a negative, so it's minus, and it's the same force, 55 newtons. I mean, same magnitude. It's a different force, but the magnitude is the same. And once again, the angle is 35. And it is also opposite, so it is also a sine. So multiply by sine 35 degrees. Now, when you look at the third force, this one, it has no y component, so you add 0. And what do the sum of y components equal? It's the mass times by the y component of acceleration. Now, it turns out, if you look, one is 55 sine 35, the other one is also 55 sine 35, but because of the minus sign, the sum of it is 0. Therefore, you have 0 equal 22 a sub y, and clearly a sub y is equal to 0, much like what we surmised at the beginning. Okay, so let's look at the x component. X component says sum f sub x is equal to m a sub x. Now, if you look at the two forces, this one and the other one, both their x components are negative. If I call this my positive direction, right? And so it will be minus 55. Now, if the y component is sine, the x component is automatically cosine. So this one force has an x component minus 55. You add the second one, which is also negative. So adding minus, you get minus. It's the same angle and same magnitude, so it is the same value. And finally, you have the snow force, the 57 newtons, which is pointing in the positive direction. So this would give you mass, which is 22 times by a sub y. Sorry, a sub x. Now, if you run to your calculator and work it out, you'll find that a sub x is going to be equal to minus 1.5 meters per second squared. Now, you will have to explain, since you choose the positive direction to the right like that, The minus is not that it is slowing down. The minus just says that the acceleration is to the left. And the diagram shows you that. Now, if you happen to choose this to be your positive x direction, and you can, and you work everything out, you will get an answer for a sub x that is positive 1.5 meters per second squared. Your a sub y would still be 0. So you would answer the question as in the sled would accelerate to the left at a rate 1.5 meters per second squared. Okay, let's see now. This is part C, the last part. A second identical sled and child is now attached via a rope to the back of the first sled. So you have a sled, first sled, and then you take a rope and you tie another sled to it. So that's the problem. It says it's not shown in the diagram. Now, the second sled, it too is subject to the same retarding force from the snow. Okay, in order to move the two sleds now, the two teenagers will have to increase their efforts and pull with a force of 100 newtons each in the same direction as before. Now, draw the free body diagram for the first sled and the free body diagram for the second sled. Make sure you label and identify all known and unknown forces. You do not have to solve for anything. Okay, so they just want you to draw free body diagrams. All right, so let's start. This is the first sled. Once again, we're looking from the top view. And right now, you have 100 newtons. They increase their effort. The other one also pulls with 100 newtons. They're still at a 35-degree angle. Okay. Now, the first sled, this one, it still has contact with the snow, so it still is subject to the 57 Newton retarding force because of the snow. Now, because of the rope is now tugging on this sled, and it would slow it down, right? I mean, if you have to pull something, you would feel that rope pulling you in the backwards direction. If you're trying to go forward and you tie something heavy to it and you try to drag it along, you can feel it tugging you, pulling you in the opposite direction. Therefore, there is another force acting on this in this direction. Now, as a point, I really should draw them together, but I separate them out slightly just so you can see that there are two forces there. We will see later that this force is called tension, but for now you can just call it force exerted by the rope on the first sled. Okay, now that's the first sled. Now let's look at the second sled. Now the second sled, you're told, experiences the same effect from the snow, right? Same retarding force from the snow. Therefore, you know that it is going to move in the forward direction. Therefore, there is a force of 57 newtons due to the snow. Now, the two teenagers are not pulling on this sled, so the second sled doesn't have those extra forces. But what it does have is the rope that is attached to it that is pulling it forward. So there is also the force due to the rope. Now, this force is F, and you will find out later that it is exactly the same value as this part of the force that's exerted on the first sled. And we will talk more about this in the next chapter, but that is the case if it turns out that the rope is massless, what we call massless. Well, that's all that they want, so you would identify that just to be complete, you say these are forces exerted by the rope. Just so that you can explain, you can be clear that that's what you mean by those F. Okay, that's it. Good luck.